Alright, so we have two warm-up problems here. You can pause me, and then you can start them. This is good review of Chapter 2. Alright, so on the first one, this is a limit rule problem. We have to understand that we can break this apart into two limits, right? X squared as one function and g of x is another. The important thing here is we realize that x squared is a polynomial. It's one of our four types of functions that's continuous in its domain, right? Trig functions, rational functions, polynomials, and roots. Those four types of functions are continuous in their domain. And when a function is continuous in its domain, we know the blue. We know the value of the limit is the value of the function. So 3 squared is simply 9. Boom. Now we got to find the limit when we read this. I look at 3. Boom. It is 3. I think the answer to this problem is 27. On our homework, we would write out the limit, including that stuff, right? We don't just write the number 27. We get all the notation. Everybody, before I go on to the next problem.
Don't erase that yet.
All right, I won't erase it, but here's the other thing you want to write in your notes. G of 3, everybody, is 1. Let's be clear, that's removable. The limit as x approaches 3 of g of x is 3. The value of the function itself is given by the dot, right? No, if we're looking at the limit here, which is traveling down the path, left hand and right hand. All right? We see it's a limit. You can't plug in h as 0 because that makes the denominator 0, can't divide by 0. We go through our rules, expand, factor, conjugate, and then finally graph and undefined. But listen, this is one we should recognize that if we expand it correctly, it should all cancel, right? It should jump out and bite us. And I check and look at a squared and 2a's. Everything else has h, so I know I did it correctly. You notice I keep writing the limit as h goes to 0, because we don't drop notation. And I get this. If h goes to 0, this goes to what? 2a minus 2. That's the answer. Now, I said you should be able to identify the function. Long term, we're going to work at this. When I look up here, I see the function as x squared minus 2x. And the original red was, and I'll go a little bit smaller here, the original red was the limit as h approaches 0 of f of a plus h minus f of a all over h. That red is those two black portions I wrote at the bottom here. And everybody, at this point, you should be able to almost picture the graph I'm going to make in your heads. And I'm going to sit here and then I'm going to draw this stinky graph, right? Where we have a plus h. I have some curve. I have f of a. I have f of a plus h. And I start with a secant line. How many times have I said this? Like 1,000, it feels like. And what am I going to do? I'm going to pull point Q back to point P by making h go to 0. I'm going to take a secant line and make it a tangent line. The secant line is the average rate of change, and the tangent line is the instantaneous rate of change. All right, and this is where we're picking up today. This is the scaffold moment. We're going to go into the lesson based on this. All right, everybody, if I want to do position versus time, and I start driving my car, and I drive my car at 10 meters per second for, on average, for 10 seconds. Does everybody agree? 10 meters per second, 10 seconds is 100 meters. Can you picture it in your head? I start at the origin. I get to 100 meters at 10 seconds, and there's a dot up here. And this is the average, guys, and I'm going to erase the line I'm going to draw here in a second. If it was 10 meters per second, and I just tromped on it, and I was going 10 meters per second the whole time, right? But everybody, you never go like that, do we? Think about it. If you start from 0, 0 at 0 velocity, you just aren't automatically going 10 meters per second. That's actually pretty fast. That's like, I don't know, 25 miles an hour. You can't just start at 25, all right? So curves never look like this. At the very least, curves look like, yeah, something like that, right? You start speeding up, you don't want to have your head jerk back into the car, do you? Right? When you tromp on it, you don't want to burn rubber. Well, maybe Cole does. But the rest of us don't want to waste our tires, all right? But the point is, we don't want to do so we're going to have some graph like this. But in real life, guys, in real life, here's the irony. We actually don't have to do this even. We could start up, slam it in reverse, go backwards a little, slam it and drive, and come back. Now that's a lot to happen in 10 seconds, do we agree? But we can do this. Does everybody see? This is a position graph. We are going forward, 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 forward. And what happens right here, there's an instant where we are going 0 miles per hour forward. But then what happens? We start traveling position-wise backwards. And then what happens? You slam it into neutral again, and you drop it and drive. And right about now, you got all the differential gear teeth hanging out in your oil bath because you slammed it right in. But everybody, this works. This is a position graph. And what the position graph is going to tell us is the position at some given time. Now, what happens here if I take 2 points? Think about this. What's the units on that secant line? What are the units on that secant line for slope? Meters per second. Guys, that's a velocity. When you look at the slope of this line, forward or backwards? Forward is positive, going forward. But if we take and put another secant line in and say, right here, what do you notice about that secant line? Negative. You're going backwards, meters per second. So when we start talking about position versus time graph, and we talk about secant and tangent lines, we can talk about what's happening now. Because the big kicker to this is if I pull the wrong points, this is a classic political move, that secant line indicates an average speed that is positive, right? I don't think that tells the right story, you guys. A better lie, if you're going to lie, how about this one? We never went backwards, right? That's what this average rate of change would tell us. That's not true either. So often what we're going to be after in this class is we are always going to have A and A plus H, and we're always going to take the limit as H goes to 0, and we're always interested about the tangent lines at any given point that we want to look at, all right? And you notice that there's some really special points, right, where it's positive, negative, 0. There's 2 zeros here, right? We have 2 changes of directions. In the instantaneous second between forward and reverse, you've got to go 0, right? Why? Because of intermediate value theory, right? It's not like you can be going positive miles an hour and then all of a sudden be going negative 10 miles an hour. You have to go through 0. This is a continuous function. We'll go through those ideas also. This is the general theory of it. The specifics here, when you talk about calculus, is that since the units is meters per second, I can just go with our standard A or A plus H, but I don't like that because I want a position function. I would argue right now this is x sub t. All right, you might say x. Well, a lot of times I use position x because the horizontal axis is given in time. Position of the particle at some time. I'm going to use that I could start at some point x, and I can go to some point x plus h. All right? Now, the only thing that you think about this, the only difference here is I've changed the letter A to the letter X. Do we really care? Not really. But it gives us a position based on that then, okay? And again, if I do this for a function, say position of t, what I can do here is I can have p of x plus h. And everybody, I am not going to spend time with this, but we can take the limit as h goes to 0, and we can find the instantaneous velocity. We can find the slope of that tangent line at x. And the awesome part about setting it up this way is that x value can be anywhere we want, right, along the domain, between 0 and 10 in this case. If I move it, and I've done this limit properly, it doesn't change anything. So when I move it to this position, and I just take the final answer, I can find the slope of that tangent line. I can create a function of the instantaneous rate of change of position versus time. But what were the units again? Meters per second. Well, guess what that gives us then?
Hey, Mr. Anderson.
Yes.
You froze, so I don't know what you were saying.
Oh, okay. How long have I been
Like hardcore.
Like, huh? How long have I been froze?
Well, like you froze just like a few seconds, but like you glitch a lot.
That's my Twitch. Okay. I'll back up. Here it comes. You guys, let's cut right to the nitty gritty. When you have a position versus time graph, all right? When you have a position versus time graph, you can find the velocity at some given point x, all right, by taking the limit, and I'll call the function f of x, just like the book does, to keep it simple, all right? You can find the velocity every time by doing this. That's the key to this. When you have a position versus time situation, you can just find the velocity. And if you want to use t instead of x, does it matter? No. T, and t, that doesn't change anything for time. But what this gives us then is that when you're given position, we can find the instantaneous velocity now. This is exactly how a laser radar gun works, guys. All right? This is how, it's not doing the average. It's sending beams so fast it takes delta H to something so horrendously small it goes to 0. This will give us, for position, all right, the instantaneous speed right now on any position graph here, okay? What we need to do is an example, right? This is hard to follow, all right? And it's best to see examples, okay? So often, again, physics nerds, all right? We can define, all this stuff is typically done in position, all right? So I can give position S sub t of some type of equation. How about this? And again, in calculus, you'll never have to derive this formula. You'll just have to use it. Now, we have to make sure we understand what I wrote on the board for position. Because I found that this gets mistaken all the time. All right? And we're going to start with that. This is the position of an object moving in a straight line. Guys, this means that this object is moving in a straight line. We're going to make a little data table in so you get a feel for what it's doing. I want to be clear. There's two types of notation. The one I just wrote is this. The 4 does not go under the 2t or the 1. Do we agree? If I want the 4 to divide the whole quantity, I would have to put parentheses around it. Do you guys agree? And if I did that, that changes it to that. That's not what I wrote this time, so we got to be real careful about our symbols of inclusion. Every year we do this, so I'm going to start from this position function. And like I said, this is the position of a particle in one direction on the x-axis. So I'm just going to give us a feel for what this particle is doing. Should I go -1 seconds? Probably not, right? Really can't have -1 seconds on the particle domain, right? Time can't be negative. And if I start doing this, all right, 7 and 9/4, 7 and 9/4. And I can keep going, all right, but that gives a rough idea. So listen, if I graph this on a horizontal axis for the position S, here's the origin 0. Because I can go to the left for position. You guys agree? I can go negative position. At time 0, it's here. then it just starts traveling. And this is definitely not the scale. Here's 3 1/4 at time 1, right? And here is 6 at time 2. And this particle is just traveling to the right. Now, the one thing we know, since it's t squared, what's happening when t gets really big? It's getting huge, right? Even though you're dividing by 4, eventually this particle really starts flying along. What I want to do is find the average speed of the particle for some spots. So we're going to, we always ask for the average speed, or the average rate of change, the average speed for some intervals. So let's find the average speed or the average velocity. Maybe we'll call it velocity today. Speed better be safe. Average velocity. And we'll do 2 intervals today. We'll do 1 to 3. And of course, we'll do A to A plus H. And guess which one I want to do first? Because this is always a 2-part question. The next part is going to be instantaneous velocity. If I want to do this problem, I always start with the variables, even though it's the second one. All right? And with that thought process, I can start defining what's happening to our graph here. Now, the big part that students always ask me, do I have to make the graph? No, you don't need the graph. You don't need the graph at all. The only thing we do it, all right, is to get a feel for what's happening here. If I want to find the average velocity now, which is actually the question, I'm going to start with A plus H. So in this case, I can do S of A plus H minus S of A all over H. And this time it's not a limit, is it? Because there's a duration of H. On the first section, I will tell you that when we get done with this, we're going to go with A equals 1, H equals 2, right? Everybody agree with that? 1 to 1 plus 2, 1 to 3. I'm going to do this in terms of the variables first. And that's the way we'll always want to do this. Now, this gets complicated, guys. Not to confuse my S's with 5's. So if I pull that function down, so I have it close, and I'm going to go back to 100%, because now it becomes a real exercise in not making math mistakes. I get 1 plus 2 times A plus H plus A plus H quantity squared over 4 minus parentheses 1 plus 2A plus A squared over 4. That's S of A in green. All over H. This is the red. This was the green. Okay?
Most other times, both the things terms are usually both negative, but this time
Because usually, from a physics standpoint, you're dealing with gravity, you throw an object in the air. This is an object, maybe an electron, going around in a circle most likely, and they're just carried about its position one way or another or something. So it's a whole different equation. It's not an object falling, that's for sure. That's why it's usually subtracted. It's usually throwing the pen in the air and letting it come back down. Okay? Everybody, this is an exercise in disaster, not to make a math mistake. I hate fractions, all right? The first thing I see is I have a divide by 4. So I either got to be very careful here or I have to get rid of it. Now, does everybody agree? I can multiply the top and bottom by 4 if I like, right? That's what I'm going to do right away so I don't screw this up. Realizing the 4 must distribute to all 6 terms, right? When I do this, all right? So when I do this, the first thing I do, so I don't screw up mathematically, guys, is I get rid of that stupid 4 division by doing that. That is my first step personally. I do not want to make a math mistake. Often I can't, all right? Once I do this, it becomes an exercise, and again, get your freshmen to come check your math. It's about squaring out the binomials correctly, everybody. And again, the beauty of this situation is, anything that doesn't have an H in it in the numerator had better cancel, right? 4, negative 4, 8A, negative 8A, positive A squared, negative A squared. 3 terms left. Oh boy, they all got H. Mr. Anderson's on fire today. Alright? Now this time, I still have a denominator, because when I cancel the H's, you guys agree I'm left with that? And that would be the answer. And the units here would be what? You want to put a unit on it, meters per second. And again, I went 100% because if I go to an entire page just for an instant, this will take a lot of paper. Alright, the good news is Mr. Anderson owns stock in companies like Kimberly-Clark and Scott Towels and Procter & Gamble. They all make paper, so when you use lots of paper, I make money. Alright? The point is we got to get to this. Now, the beauty of this is by doing this one first. Alright, and I'm going to take care of all these steps in the middle. I'm just going to group them and make them small so we can have some more white. Boom. I'm going to move this up. Alright, I know that the average velocity for this situation equals that. We just proved it, alright, for the function we had. So if I come back up again, alright, and I come down the page, here I sit. Well, this is the answer. The red here is the answer to this. Now, in about 3 seconds, I should be able to do the first one. Alright, and I'll do that in, I don't know, black. So I have 8 plus 2 times 1 plus 2 all over 4. And that's, I think the answer there is 12 in the numerator divided by 4. How about 3 meters per second? Alright. And that should make sense to you, because let's go back up to our table. And the reason I made the table here is this. 1 and 3 1/4, 3 and 9 1/4. 9 1/4 minus 3 1/4 is 6. 3 minus 1 is 2. 6 divided by 2 is 3. Okay? Doesn't matter how you slice this, how you dice this, alright? The most important part, the reason we developed this red equation now, though, is for the next question, which is, how fast am I going now? What's the instantaneous velocity at, say, time A? So I want the instantaneous velocity. And instead of developing, doing it for 1, I want that at time equals A. Well, what you have to realize now is you've done all this legwork for a reason. Alright? You have made this statement right here. And now we can use this. We should realize now that to go from the average rate of change to the instantaneous, we just have to bring Q back to P. We just have to take the limit as H goes to 0. So I look at this original one, say, oh, yep, I'm going to take the limit as H goes to 0 of what? Of 8 plus 2A plus H all over 4. Guys, bottom's not 0. H goes to 0. Guess what that is? 8 plus 2A. If you want to know the instantaneous speed at time equals 1, replace A with over 4. Over 4. Sorry. If you want to do it at time equals 1, it's just 10/4.
Mr. Anderson.
Yes. I can hear you. Okay, that's what you gotta do. Ask me. Yep.
Yeah. What time is it now?
2:56.
Oh.
2:59. No, our fridge is shutting down.
Oh no! All right. Well, I'm recording this, so you guys can't see anything right now, can you?
Not the moment. Oh, we don't have one going right now. Just wait.
All right. I'm gonna pause the. Let's hang on. I'm gonna pause the video too.